Welcome to Module 37 of Database Management Systems course in the IIT Madras online BSc program. We have been discussing about fundamentals of algorithms and data structure, which you have already done in your algorithms course, but we are just doing a quick recap of the key ideas and key data structure which will be frequently needed for our design and optimization of the physical storage. So, we talked about the analysis of an algorithm, particularly the execution time and space. We have recapped on the asymptotic growth and looked at some of the provided a chart of complexity for the common data structures and common sorting algorithms. In this module, we will again talk specifically about data structures, simple data structures. We will review the linear data structures and also the linear and binary search. So, that is what is on the agenda. So, a data structure as you know specifies a way of organizing and storing in memory data that enables efficient access and modification of the data, right. You are studying database. So, you will often be encountering this question that what is the difference between a database and a data structure. Be prepared to address that. A data structure which broadly we talk of is necessarily in memory, that is it exists as long as the program is in execution, and a data structure has a persistency. There are other factors also, but this is a key difference. The data structure typically can be classified in two ways. One is linear data structure, the other is non-linear data structures. We will take one by one. Now, in designer's perspective, what is a data structure? It is a container. It must contain data because it is a data structure. So, the primary of it is a container, and it has a set of typical operations. The operations that you would like to do efficiently with an efficient container storage. So, this combination of what is the kind of container and what are the type of operations you want to do tells you specifically about the data structure. Now, there are plethora of data structures, but we are focusing on the fundamental ones, particularly relating to data management, because we are doing it as a precursor to the physical storage design. So, in relation to data management, I am immediately not talking about what the container could be, it could vary, and as we will go finally to the database physical layer, we will see that it will have containers which are no more in memory. To give you persistency, they are outside of the memory system, they are in the permanent storage and so on. But the key operations of interest are these 5. Certainly, you need to start creating it somewhere. Let us say create. You would like to add a data, insert, delete, remove a data, find a data, right. So, we can talk about update, but we will not specifically say that, because an update is kind of a search, delete, insert. Like by this you can actually have an update, though you may have direct update procedures also. And finally, you close the data structure, wrap up whenever it is not required. So, when we talk about efficiency, efficient access, what we mean is it is efficient, the data structure is efficient in terms of time and space for these operations. Efficiency is not absolute. Some data structure is efficient for some operation, some is efficient for some other operation, some is efficient in space, some may be more efficient in time, and so on and so forth. These factors will have to be all kept in mind as we go over this discussion. So, first we talk about linear data structures. A linear data structure has data elements arranged in a linear sequential order, right? And in some way there is a way to know, if you know a particular data element, then there is a way to know the next data element. So, if you look at the computer organization, there are two ways. One is purely sequential, that is like memory, where you have a one after the other, you have the data and they have addresses. Where is the next data element? Where this data element ends. They are necessarily consecutive. So, we can also go to any arbitrary data element by looking at by referring the index, because I know if I know where this starts, by knowing it is the fourth element, I will know what this offset is and I can directly go there. So, this is indexed, this is random access. What I am trying to say is, before coming to data structure, I am just trying to see what does the computer organization give us, because all our data structure will have to be based on that. The other one that we have is referential, right, which is I have a location, memory location, which has an address of the memory location. So, if I know the address here, I can go to this element. So, this is by, you can say call it a reference, you can call it a pointer, but it is referential, that is I can use the memory addresses to go from one data to the other. So, here I have to know with every data element as to what is the address where the next data element will be available. That is the basic concept of the referential mechanism. These are the two fundamental mechanisms available by computer organization. So, all your data structures are based on these two concepts, right. So, based on that we have arrays, which is indexed sequential, we have linked list, which is referential, and using those we could build queue or stack, which could either use indexed sequential or it could use the referential structure, right. Arrays, you all know, it's consecutive locations. So, stored in contiguous location, it can be randomly accessed and so on. In linked list, the data elements are not stored in contiguous location, rather each element has a link, has a reference, has a pointer to the location in that. Now, when we talk about other data structures like queue and stack, we will first talk about the operation. So, what are the operations here? Let us say, what is the operation in an array? The operation in an array, I can create an array, I can insert an element in the array, I can delete an element from the array, I can search for an element in the array. In the linked list, I can create a linked list, and interestingly, I can keep on creating new data nodes in the linked list, which is an additional operation, which array does not have. But in addition, I can insert a value, I can delete, I can search, all these I can do. But so in array and linked list, we have the container and the operations both defined together. In case of a queue or stack, we do not talk about the container primarily. We primarily talk of the operations. So, in queue, what we say, it is a first in, first out. So, a queue, if I remove an element from the queue, then it will always be the oldest element residing in the queue. That is, the insertion and deletions take place in the same order. So, it is a first in, first out. Whereas in a stack, when I remove an element, I will always get the last inserted element, last in, first out. It is not typical for a queue or a stack to have any other kind of, say, find operation. Finding an element in stack is not what you do. Finding an element in queue, you do not do. Instead, you have in queue, you say what is the front element, that if I remove, what is the next person who is going to get to the counter. In stack, you say what is the topmost element. So, it's operations have a little different connotation. Naturally, you will have a create, you will have a closure. But what is significant to see that the basic definition of a queue or a stack does not depend on the container. It is only on the operations. Now, a queue can be on an array or a linked list. It could be circular in an array and so on and so forth. So, container could vary, container structure could vary, but the operations will have to remain same. That is what defines the data structure. Similarly, for the stack, you can have a stack on an array, stack on a linked list. Right? You know that, know all this. I am just trying to, summarize what you know. So, array is indexed. You already know that on one side you have the array indices, on the other side you have the physical memory address, and inside you have the containers. So, you can, it is computer organization wise, it is implemented in a way so that the accessing every element is very fast. That is order 1. It is a constant time, because you know this, arithmetically you can compute the access and get this address. It is just one memory address. Very simple. Arrays have fixed size. They are not flexible. Right? You may have heard of some, variable size array and all that, but those are implementation details, but conceptually an array is a fixed size. So, array may have, if I decide to use the space from the left end, the 0 index end, then array will have some unused space at the towards the end, and as long as there is space, I can use that array. So, if I want to do insertion or deletion, it is very easy if I am inserting at the end, because there is some empty space, I just put the element there, or if I am removing from the end, it is the last element, so I remove. So, that is constant time. But if I have to insert at an arbitrary position, as in here, then I have a problem, because I have to create space for the element I want to insert. So, I have to move all of these right. So, I have to copy this here, copy this here, copy this here, copy this here, and only then I have the space for f. So, the worst case would be when I want to insert in the front, I have to move all the elements. So, naturally insertion in an array becomes order n in general. Similarly, removal will be order n as well, because after removing this, you have to move these elements left towards back, so that you satisfy the assumption that you have elements packed from index 0 to a certain point. So, array is good for access, but not so good for insert and delete. Now, let us move on to linked list. They are not in contiguous location. So, every data has two parts. One is the data and another is the link, where the next data happens. And to know where the first data is, you have a special storage called header. Right? So, in this, naturally, you will have only those many data nodes as there is data, unlike array where you will have extra. So, when do you say there is nothing more to find? Just you put a 0. That is again a system specification, comes from computer organization. Right? So, this is your linked list, you know. So, it is flexible in size, but the random access that you could have in an array is no more possible, because you do not know the address of the third element. The address of the third element is known by the second element's link. The address of the second element is known in the first element's link. The address of the first element is known in the header. So, you will have to necessarily start from the header and go there. So, immediately you can see that access turns out to be order n, because you could be looking for accessing the last element. So, you have to start in the header, pass through the entire list, order n, expansive. In array it was order 1. So, if you look at insertion of an element in the beginning, it is very easy. You have a node, you just, all that you need to do is to adjust these pointers. So, A was pointing, what is that? A was pointing to B and header was pointing to A. Instead, you want it at the front. So, this one you want at the front. So, what you have to make? You have to make header point to this and F points to A. So, you can make F points to A and then just change the header pointer. Very simple, constant time. Similar thing you can think of in terms of the removal, if you are removing the head node. Right? Constant time again. Now, what if you want to insert at an arbitrary position? So, the first assumption would be that we have already seen that the access is order n. Right. So, we cannot mix up with that. What we will say is, if I know what to insert, I will assume that I know what to insert, then it is very easy to insert. If I know to insert at the end, then all that I need to know is this node. If I know this node, then insertion is just putting this link. But if I do not, I will need linear time to come to this node, the last node. Right? So, assuming that I know the last node, it is a constant time operation. Similarly, for removing from the end, all that I need to know is the node before the last node. Right? I cannot remove the last node by itself, because it is being referenced from the previous node. So, I need to to remove this node, I need to know this node. So, if I assume that I know this node, then it is a constant time. All that I need to do is to set this to null and get rid of the last node. Similar observations can be made at intermediate position. If I know the position where I want to do the node, then all that it needs, if I have to insert this F, all that I need is to adjust this and adjust this. That F has to, the node after which F has to come, that its pointer should be set to F and F's pointer should be set to the node it was originally pointing to, right? Constant time. But the key of all of these is the fact that I need to know the node where I am actually doing the insert. Similarly, remove would be also constant time, order 1, if I know the node before the node that I want to remove. So, we can see that to sum up, in terms of array, the access is very efficient, order 1, the insert and delete are order n, whereas in a linked list, access is order n, but insert delete, once you know the position, is very efficient, it is order 1. So, you have a trade off in that way. Let us see, let us leave with it. So, the other common operation that is left is search, how to find, right. That is different from access. In access, you have the index and you are finding. So, it is positional, but search is by value. So, it is associative search, that given the content you find out where does it exist. Right? So, one way you could do is do a linear search. You are given an element, you start and check with every element in an array. You will be able to do that and if the element exists, you will be able to say that it exists. If it does not, if you have exhausted the whole array, you will say it does not exist. Right? So, You can do a linear search, which will obviously be order n. Now, here is a simple Python code which lets you do that. The other option that you know, I'm sure you know, is there is a better way to search this. What do? Assuming that the elements that you want to store and search can be ordered. I mean, one can be considered to be less than the other. There is some way to compare them. What you do is you sort the elements in certain order, increasing or decreasing, whatever, in the array. So, there is a setup time that is required for this. So, create of this is going to take more time than just an array, because it is just not storing the elements, you have to also sort them so that you can do this kind of a search. So, that setup is going to take you order n log n time. But once the elements are sorted and you are given to search for something, you have a very simple strategy. Is that you look for, instead of starting from the beginning to end, you look for the middle element and you compare with the middle element. You know they are sorted, say in this case they are sorted in increasing order. You are looking for I. So, as you compare for the middle element, you see it is D. Now, what is the assertion that you can make? Is since they are increasingly ordered and I is greater than D, I can never, if it at all happens, it can never happen on the left side. So, you remove the left side, or not physically remove it from the consideration, and therefore, your problem reduces to searching for I in this part of the array, which is half the size. And then you again look at the middle, it is even. So, you have to look at either the I node or the M node anyway. If you happen to look here, then you will immediately find I and you will say it exists. If you do not find, you will again half, because it can either be on the left or be on the right. Finally, given, so first you search within a array of size n, then in an array of size n by 2, then in an array of size n by 2 square, you keep on doing till you will obviously be left with an array of size 1. It either exists that, it either matches that or it does not. If it does not, it does not exist. Otherwise, it matches somewhere in between. So, as many times you will do this division and matching is your complexity of operation. How many times can you divide n by 2 so that it becomes 1? That in fact is the value of log n. Incidentally, when I write log n, what I mean is log to the base 2n. When I write Lg, it means, and when I write log, it means the natural logarithm. So, Lg is what is very common. So, how many times can you divide? If I take 16, I can divide by 2, get 8 first, divide 8 by 2, get 4 second, divide 4 by 2, get 2 third, divide 2 by 2, get 1 fourth. So, I have got to 1. So, how many steps? 4. What is log 16 base 2? Is 4. That is a power that you will have to take of 2 to get to 16. So, which says that the beauty of this search, naturally called the binary search, is you can find a key if in or determine that it does not exist in log n time. Right? So, these are the two ways to do the basic search mechanism, and there is a Python code. Now, if we put it to context, then for search, if I have linear, if I do linear, let me write it more cleanly. So, if I do linear search, I can do it in an array which could be ordered or unordered, it does not matter. And in both cases, it is order n. If I do a binary search, then if it is ordered, then I can do in order log n. If it is unordered, I cannot do it. If I have a linked list, it can be ordered, it can be unordered. The linear search will always be order n. Binary search simply cannot be done even if it is ordered, because to get to the middle, I need to have an access to the middle, and that access is itself order n. Insert, in an array it is order n, in an unordered array it is order 1. Why is it order 1? Because if the array is not ordered, then I can insert it anywhere, I can insert it at the end. The deletion, the insertion in linked list is order 1, whether it is ordered or unordered. How about deletion? In an array, it is order n, whether it is ordered or it is not ordered, because I have to delete from wherever it is and move the rest. Whereas on linked list, it has order 1. So, you can see of my 3 major operations, if one is good in one data structure, like insert or delete is good in linked list, the other, the search or find, is bad, it is order n. And if search is good in array, the insert delete is bad. So, my conclusion is that my linear data structure has contradicting performance. It does not give me a complete performance, so that all of insert, delete, search can be done efficiently. Okay, I mean, I am not saying that it has to be order 1 all the time, but at least it has to be order log n. Order n is too expensive to work with, and you should look at the growth chart again to see what is the great difference between order n and order log n. Right? So, that is what we have recapped today, reintroducing the data structure, I should say, and reviewing array, list, stack, queue, and so on. And naturally, if you look at the complexity of the stack operations and queue operations, whether you do them with an array or with a linked list, you will see that the basic pop, push, top, or add, delete, remove, add, delete, check front item in queue, all of them we have to order 1, the constant time. Okay, so with that, I will we close this module. Thank you for your attention, and we will meet in the next module to talk about the nonlinear data structures.